Welcome back. So now we will be discussing that what is the significance of knowing the velocity profile in pressure flow. Okay. So till now we have been talking about pressure flow inside a pipe. So this discussion we will be having based on the pipe flow, let us say. So the term we are going to discuss here is the Fanning's friction factor. So now before talking about Fanning's friction factor, let us recollect some of our earlier concepts. First one is expression for shear stress related to fluid flow. Fluid is flowing in x direction and we are estimating the shear in radial direction. So expression is delta P by 2L into R. So here again this diagram is there to explain it. Let us see, you see, this is the radius of the tube. So total length will be actually twice R, means the diameter of the tube. Velocity, fluid is flowing in x direction, means it has got component Vx. Okay. Now here what we are saying that we are having some shear between the layers. Okay. So let us just talk of laminar flow, where actually we can consider flow of fluid as layer by layer. Okay, there. So what is the rate of shear? So that this is the expression. So here delta P by 2L, or rather delta P by L, actually what it means, it is again actually explained. Let us say it is flowing through a fluid is flowing through a pipe. At one end you are applying pressure P1 and from the other end we are applying pressure P2. So when P1 is greater than P2, then fluid is flowing from left to right. So the pressure drop, or rather pressure gradient here, is basically delta P by L. So delta P by L is P1 minus P2 by L, and mathematically it is negative of dP dx, means this gradient is negative. I can show here this in the direction of flow pressure value decreases. So that's why actually see it is negative of dP dx, means dP dx will be having some negative value. Okay, so that's pressure drop. So now another we'll have means expression, actually we have already talked that for laminar flow, velocity at in x direction at any location R can be estimated by this expression, V maximum multiplied by 1 minus R by R square. Okay, so this is square of this ratio only. Okay, so now here what is the value of V maximum? V maximum is delta P by L into R square divided by 4 mu. Okay, it is actually rated delta P R square by 4 mu L. Now V average, actually that we have already done, that V average in case of laminar flow in a pipe, horizontal pipe, is actually half of the V maximum. So it is, this denominator becomes 8 mu L, the rest remains same, delta P R square by 8 mu L. So now let us try to apply these concepts for our particular purpose, where actually see we are talking about what is the application of it. The application is that actually see how much pressure you will be requiring to make the fluid to flow. Okay, so now we will have to know that actually what is holding the tube back. So where this tube is being held back is this actually at these outermost positions. So that is called the wall shear. So now we are going to estimate the term called wall shear. So wall shear is value of tau Rx when R is equal to capital R. So this is delta P by 2L into capital R. So this expression only R is getting replaced. Okay. Now another question is whether actually see this wall shear is going to give the reflection, actually how much resistance is there to the flow, and then actually based on that we are going to estimate how much effort or pumping action we will have to give to overcome this means resistance. So So the question is, what happens if the average velocity changes? So whether this wall shear is a function of V average, and of course answer is yes. We can just verify very simply tau expression of tau omega, and if we try to divide it with the expression for V average, we get this particular value, which is basically 4 mu by r. So this is quite crucial. Actually, we should remember this is the ratio of this wall shear to V average, which is 4 mu by r. So 4 mu by r. So this is minor modified. 4 mu by r can be written as 8 mu by d also. So another way of writing it is wall shear is equal to 4 mu into V average by r, and mu is taken outside, then 8 times of V average by d. Now compare it with the original expression, actually based on which we make all such calculation, that shear stress is equal to coefficient of viscosity multiplied by shear rate, multiplied by shear rate. So shear stress is equal to mu into a factor. So this name of that factor is basically shear rate. So now here is the left hand side is the wall shear, and the right hand side is the coefficient of viscosity multiplied by a factor 8 times of V average by d. And when we apply that principle of actually stress is equal to shear rate multiplied by coefficient of viscosity, then actually see 8 times of V average by d becomes the wall shear rate. Okay, so just actually this is, I will recollect, shear stress is equal to mu into shear rate. So it means minus dV dr at location of r by r. What will be its value? Its value is 8 times of V average by d. Okay, that the same thing we can write in terms of radius as well, as 4 times of V average by r. Now some more detail about this tau w. You see, when there will be some fluid flow happening, okay, so probably see people may not be very much interested to know that what is the velocity profile of it, and actually they will like to get a ready-made expression or you see handy expression, so that actually even without doing this integration of flow profile, they can estimate this force requirement. Okay, so therefore a concept is coming which is called actually Fanning's friction factor, the topic of this discussion. So okay, so now first thing is that is a drag force per weighted area is defined as actually this idea is to define Fanning's friction factor. Okay, so how it is defined? That drag force is basically a product of, remember, drag force per unit weighted area is a product of two factors. One is the F and the velocity head or the kinetic energy head. So this drag force per weighted area, or that tau w, is a product of F into this velocity head or kinetic energy head. Okay, so therefore this expression for Fanning's friction factor, our topic for this discussion, is a drag force divided by the kinetic energy head. That means tau w divided by half rho v square by 2. Now here actually you should always note that is a V average. It is what value of velocity you should take while describing the kinetic energy term. It is the average velocity, and average velocity is experimental determination is very easy. Just collect how much fluid is coming out from a tube in a given time and try to find out the volume divided by cross-sectional area of the tube divided by unit. So then you can get this V average. Okay. Then of course this is little bit manipulated, tau omega by V average. Somewhere we have done, na? So how they are related. Wall shear is related to V average. We know that expression also, and denominator is half rho V average. So this earlier expression you can remember that tau w or wall shear by V average, we got an expression 8 mu by d or 4 mu by r. Okay, so then the expression for F becomes 8 mu by d divided by half rho V average square. So now 2 goes up. Okay, 2 from the denominator goes up, and it is basically 16. Okay, I think rho v d by mu, yeah, something 16 rho v 16, it will be 16 mu into rho v d, that is equal to 16 divided by rho v average d by mu. Okay, this one. So now it is basically, see, if we know the definition of Reynolds number, basically what is there in the denominator? The denominator is the rho into v average into d divided by mu. For circular pipe, d means the actually see pipe diameter. Okay, so rho v d by mu, it is called the Reynolds number. So it means friction factor is basically 16 by Reynolds number. Okay, of course it is for laminar flow. So now that is a quite interesting information, and that was our idea actually. See, we want to know a factor named as a Fanning's friction factor, that is basically 16 by Reynolds number. Now if you know the value of friction factor, then how you can obtain the pressure drop? So now again, you see, let us come back to this definition of F. It is tau W divided by kinetic energy. Tau W divided by kinetic energy. So tau W is delta P R by 2L and kinetic energy term. Okay, so from here we are interested to know the pressure drop basically. So pressure drop we can write it 2FL by R kinetic energy, which is 4 by D FL kinetic energy, and that is modified as 4FL by D into kinetic energy term. So now if you know the value of friction factor, then you can estimate the associated pressure drop. So this is quite important. So friction pressure drop inside a tube or any conduit, actually you can always estimate it by using this principle. So in case of circular conduit, actually this D will be your actual diameter of the tube, this F is the Fanning's friction factor, and L is the length of flow, and this is the kinetic energy here. Okay, so now Fanning's friction factor is available in the form of graphical representation, and if we want to represent it graphically, actually how it will appear, so you can just see F is equal to 16 by Reynolds number. So if we take log for both the sides, it is log F is equal to log 16, which is a constant, minus log of Reynolds number. So now log scale Reynolds number in the x-axis and Reynolds number, friction factor in the F in log in y-axis. So you are going to get a straight line with negative slope. Okay, so then this will be valid, remember, as we have said, that this will be valid for this laminar regime only. So what happens beyond laminar regime, that is not apparent from these derivations, but for your understanding you would note that actually see in the turbulent regime they are constant. This value of F is constant, and we can read from handbooks where actually see tabulated values of F will be there, which are determined experimentally, and it has been seen that actually that F value depends not on Reynolds number, rather actually relative roughness of the tube material. Okay, so that you can refer to any standard book and you can obtain there. And up to here, actually see what happens in case of laminar flow. So that we can obtain means you see mathematically as well, that the value of F is inversely related to the Reynolds number. As Reynolds number increases, the value of friction factor decreases. So that's all. We can refer to the books containing, or even our textbook, this information is given, the chart is given, so you are advised to refer to that. Thank you.